Okay, get ready, get ready. I'm going to show you how the nucleus of all atoms are constructed, and they are dipoles. Now, the traditional standard for the nucleus is it's made up of giant protons and giant neutrons, basically the same size, only the neutron has exactly one extra electron. And how do I know that? Because it weighs exactly the same weight as an electron, the increase in weight for a neutron. It's like 0.000585, I can't remember. It's way down in the atomic mass units. They don't even consider an electron to have any weight to speak of because it's so small. However, the electrons are two parts, and they're not two big parts like this. They're one big black part, and they're one fluffy little white part. And I will show that, and have shown it, but I'll show it to you again. Okay, I'm about to freak you out. This is a toy, and it is literally identical to the nucleus of all atoms, and nobody has a clue. The reason it's identical to all atoms is because the central core is a big, heavy-duty positive sucker. It just sucks all these negatives in. These are nothing more than negatives attracted to the core of a positive. That positive is so attractive that it will try to bring in more negatives. And these have fulfilled its requirement, and they say no more. No more come in here. And that is exactly what you are about to see. Latham's crazy machines, absolutely fabulous. It's called incredible tractor beam magnets. They think it's a toy. It is not a toy. This is a nuclear core. And watch what happens when another electron comes in. You see it? Anybody that understands quantum knows that your electrons float around the core of the nucleus. Why do they do that? If this was a big positive, these were little negatives, they just snap together. It is impossible. This has to be a dipole. And it has to be more attractive in the core than it is outside. So the core is still trying to drag more negatives in, but these negatives say, no, no, you cannot come in here. We have plenty surrounded here. Don't come in here. And it says, well, what do you want me to do? And it says, I want to get into that center. And it says, you can't get to the center. We won't let you. And that's called the quantum distance. It says, well, if you stay right there, you can stay there. I know you want to get in there, and you want to get in so hard, and we want to push you so hard. This is push to shove. I'm trying to push my way in. You're shoving me back out. Push to shove. It creates an atomic angstrom unit distance. Angstrom units are measured in very, very tiny, tiny, tiny little distances. Obviously, you can't see. This will never do an angstrom unit. Angstrom units are down to the point where you can't even see them. Well, you're never going to see them because they're in the nucleus. Now, you can only see them with some of these new tools that we have that really sort of show what the nucleus is designed like. Well, I'm going to show you the electrons. We've seen these. And we see exactly what happens here. It's not a big mystery anymore. The mystery is that we can't get anybody to look at it. But here's what's happening. It'll stay there forever. This guy can shake it around and bounce it. Now, here's what happens when he goes fast. All right, let's just stop for a second. This is just sort of walking around, like bouncing around, this thing rolling around, doing this and that. No big deal. But then you hit it with a heater. It starts getting hot. And it's going to start getting hot right now. He's going to start shaking and shoving. This is push to shove. Boom, 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 boom. See? Now watch that electron move. You see it moving its orbits? This is the bounce. And this bounce determines the light that we see. You say, oh, Roger, how can that bounce determine the light? Well, the bounce is frequency. The bounce is how hard that spin off of the particle is. It's going to spin out of there. And when it does, if it's spinning real fast, it's in a blue range. If it's spinning kind of slow, it's in the red range. Simple as that. And we're shining the same light on the same stuff. All right, so let's take this chart right here. All right, we're shining the same light on it. Why are all these different colors? How come they're different colors? Why doesn't the light just shine back the same as the light we're shining at it? The reason is it's chemistry. This bounces back different than this. The blue bounces a little more intensely back than the yellow and the down into the red range. They don't bounce as fast. And I can prove this because I could show red versus green bounce. We've gotten down into the nuclear core and seen, well, we've gotten down into light and seen the actual particles. And I think I've shown you that before, but I'm certainly going to show you again. Okay, my friends, I'm going to make this real quick and simple. This is an article by Don Lincoln, who is from Fermilab, and he's talking about the field of particle physics is full of confusing dichotomies. Fermion versus boson, hadron versus lepton, paper versus plastic. Okay, not the last one. That's a little joke of his. You can add yet another to the list, extended particle versus point-like particles. Here's what he's got. He's showing this extended particle, which never changes size and has a tiny little glow around it. It's just black. And that, to me, is the muon, and it is dark matter. This is the point-like particle. It's just a glowy thing. It can get smaller. It can get bigger. Now, I'm going to cut right to the chase because it's a little confusing, but it's not that bad. Now, let's just get right down to summary because I'm going to show you those particles. We have actually seen them. And it says, in summary, the extended particles, that black one, is a fixed size. It never changes the size. Never changes. Although they may have a fuzzy edge around it. Okay? So there'll be a little fuzzy edge around it, and I'm going to show you that. Now, the point-like particles are mathematical abstractions. They don't really know. They know they can change them mathematically, how big and small they are and so forth, but they don't even know if they are a particle. It says with zero size. Now, how could you be a zero size and create a field? That's my problem with this. But I can't discount it either. So he says, then this is Don Lincoln again. He says, but even zero-size particles have an extended effect, which is the field, due to the effect of the field surrounding them. Well, surrounding what? But that's the thing that we have to look into. Now, I haven't been successful at getting through, and I'm hoping you guys will contact Fermilab. And here it is. Let me get right up close and personal with that so that you can see that email. And please email Don or whoever you can at Fermilab and ask him to take a look at my work. I'll show you these particles, and they're exactly the same that Don is looking for. And they are the muons and the electron neutrinos and the electron showers. I'll show them right now. All right, this is a photon of light, and the only reason we can see it is because we created an extreme amount of luminosity by putting it through the venturi. I'll show you all these things in a moment. And CMOS smartphones can actually see these. They work exactly the same as the best, biggest, equipment in the world, because they're using exactly the same technology. And we're going right on top of the power source, so that we're right on there watching these events occur just explosively. Now, what did Don Lincoln talk about? He talked about that big black particle, extended particle he called it, or a muon, boson, carrier particle, they call it. Okay, and what is it carrying? It's carrying one of these. And what is that? That's the exploder. This is the point particle he talked about. And a point particle, I agree with him. I can't see where there's any size to it, because it can go big, it can go small, it can concuss, it can turn into showers. I don't understand that. This is what I need Don to help us with, to understand what we're looking at here. But I can see this is exactly what he talked about, the glowy edge around the black particle. They never change size. And then what we created was a device that excluded these black ones and allowed the white ones to come through. So we actually separated those. That's called fission. And when they came back together, that's fusion. Normally that's an extremely high energy source, and that's what everybody's trying to do, is create cold fission and fusion. And we did that. Now, we're in the subatomic range. They want to do it with big chunks so that they reduce them to helium. Here's what they want to do. Hold on. If you're not a geek, this may not be your right place today. Now, they're taking heavy hydrogen, which means hydrogen, it's not just a one proton hydrogen. So it has a bunch of extra stuff to it. And they're trying to crunch them together so hard that they turn into helium. So instead of having one proton here making a hydrogen, right now they have a whole bunch of garbage together that is really a hydrogen, but it's not really a hydrogen. So they can break it apart. When they break it apart, when they come back together, fuse back together, they turn into a helium, which has two, well, it's got four really total. It's got two protons, they call it, and two neutrons. All right, so they're forcing it to do that and then give up a whole bunch of electrons. Basically, that's what they're doing. They're letting it give up electrons. What do the electrons do? They are heat. Electrons are heat. And that's these. These right here, they're giving up. And we can give these up through our venturi. Now again, if you're not a geek, this is probably going to be not your best day here. Now, they say that they're taking stuff like this and smashing them into bits, and then when they come back together, they form a stable helium, and there's a whole bunch of extra stuff. Well, I can't disagree with that, because all they did really was like cause a whole bunch of little particles to leave, because they were excess anyway. And then these turned into electricity. They spit out one at a time into electricity. But they are these. Now, I don't know if they're only these, or are they this particle, which is, in my world, an electron. Here's my model right here. You see these here. This is the photon. Well, what is a photon? It's light. Light, they don't even know if light is a particle or a wave at this point. Nobody really has a good fix on this. I could tell you it is a particle and a wave, because the magnetic field around it, as it goes this way, creates a wave. And the particle is the creator of the wave. So you have a particle-wave duality. All right? Now, half of an electron, of a photon, in my mind, is what we always called an electron. And what did we always call an electron? We always thought of an electron as being a sparky little piece of juice, something that heats things up, something that burns things, something that flows through copper wire, something that rotates around a big nucleus like this, just a tiny little nothing that just floats around there, but has a negative charge equal to the proton. It's just, it never worked. I knew it never worked. In 1970, I was in physics pretty deep, and my theory ended up saying that light is atomic vapor, which means atomic means it's a dipole. It has a positive and a negative, and it is the vapor of matter. That's all it is. You can put that stuff back together, and if you put it back together in a certain way, it's going to be zinc. If you put it back together in another way, it's going to be copper. If you put it back in another way, it's going to be calcium. It doesn't matter. These particles are just one big ball of electrons. An electron consists of the dark and the bright part. All right, so every electron, they call them neutrinos, consists of a muon neutrino, electron neutrino. All right, so that's the electron. You take 1,839 of these and add them together in a ball like this. That turns out to be a proton. And it's a positively charged particle. It means it will take one more to go into 1840, makes it neutral. And this is, I think, it could be 1836 and 1837, 1838. It's right in that area. But I'm going with 1839 for a proton, 1840 for a neutron. All right, and an electron is just one. And they float around the nucleus trying to get in, because the nucleus says, hey, I want some more electrons. And the guys that are surrounding the nucleus say, no, that's it. We got plenty of guys out here right now. Case is closed for that. And then they just hang out around, and they are the orbiting electrons in their quantum states. And if there's enough of them around it, it'll say, okay, no more in this region. Make another region out there, because they'll push against these. So it's push to shove, push to shove, push to shove, push to shove. So you can have layer after layer after layer of electrons. And that's what happens when you get into plutonium and uranium. They have a core like this in the center. So they really want to suck electrons. Well, you can only have a certain number real close, and then another number on another layer, and then like a Russian doll, all bigger and bigger and bigger. All right, and you can't say anything about Russians today after this Ukraine thing. I mean, they are the nicest people too. The people in Russia are nice. I can't understand this. This is just terrible. This is not going to go down in history well, Mr. Putin. That's just another day. Anyway, this is... Boy, I got to stop for a second. All right, I think I've shown enough so you understand that we are being able to do fission and fusion. And that hopefully will make a whole difference in the way energy is used and produced. And hopefully it's 100% free energy. Because if this works, what I'm saying is if you have fission and fusion, which is exactly what CERN and all the rest of them is talking about, you get extreme amounts of energy. If that's true, we should be able to harvest that energy. All of these are off-the-shelf components. We should be able to do this within a month. We'll know one way or the other, will it work or not. I'm starting to think I might be wrong. I could be very well wrong, because I am in the subatomic range. They are in the atomic range. They're starting with gigantic balls like this. I'm starting with one of these. I'm starting with one of these particles right here. That's it for me. They're hitting these things head on, one here and one here, head on, and creating all this garbage and chunks of pieces of this that are 50, 100, 200, 60 of them, 5 of them, 10 of them. That's called nuclear decay, nuclear debris. It's and then it's radioactive, because it can't stay in those states. They have to be in these, what they call periods. That's the periodic table. And all they are is bigger and bigger balls. And they get stable at certain frequencies. I'll show you that in another toy experiment. All right, and all I want to say about the Ukraine thing is it's tearing me up something terrible, and it's ruining my research, because I get starting to think about it, and it really throws me off track. And violence is never the way. And we all think we're doing what we can for our country and our way of life and everything, but I just don't know what to say. It's just not the way, Mr. Putin. Violence does not work. You're going to get to the end of the story one way or the other, and we're just going to have tragedy at the end here. It's not going to be a pleasant ending. Boy, I tell you. Oh, man. All right, I'm going to leave that in. I must have done this 20 times, and I start going off on this thing about Ukraine. Well, I'm going to tell you something. At some point, we're all going to have free energy, and at that point, that stranglehold, which the United States and Venezuela and Russia and all these places have a stranglehold on the rest of the world because of energy, and that creates a very tough dynamic. If everybody had their own free, I mean free, I'm talking 100% free. Once you build these devices, that's it. They just work forever. They give you free energy for the rest of your life. You don't have to pull over your cars. You don't have to even park the airplanes. You just let them run. And it's off the grid stuff too, so you don't have to, but there would be so much free energy around, you could create grid infrastructures all you wanted. Just about anything would be possible if we all had free energy, and there would be no competition between nations, because everybody could build their own stuff, because you'd have all kind of extra energy. It's the unavailability of resources in most impoverished countries, and in developing countries, the unavailability of resources puts them at the feet of somebody that has the sources. You got the sources, you control the world basically. If you have energy, Everybody has it. There's no patents on this. Anybody can do this. I've been showing this for at least 7 years now. And Rod Warren was the guy that just accidentally devised this. And he only did it because he was trying to do a double slit experiment, and all he did was make one slit, and he made it into a venturi instead of a flat plate. And when he made it into the venturi, all the fields crushed and did exactly what CERN wants to see. And it made the electron showers. And at the same time divided and created sterile muons, which is these. Sterile means they're all by themselves. And the black or the white particle had left and turned into a shower. So once the energy crisis is changed, the world political situation changes, humanity changes. You could put these things and take them into outer space. You want to go there, I don't care, go anywhere you want with them. Because they're self-contained units. And it would be, this is what I'd use for a demonstration. It's just a Geiger counter, but you'd have a couple little controls here to select whether you wanted AC, DC, 120, 220, 50 volts, 50 cycles, 60 cycles, AC, DC, anything you wanted. Once you create that free energy, all those are is electrons, and they are powerful. They have extreme burn capability. And I can show that as well, because the first thing to hit in a nuclear explosion is the white particles, which surround the dark matter. So they're the first to go. And all they do is burn. Let me show you that. Alright, I'm going to make this extremely simple. What they do with an atomic bomb is they have so many particles that they're already starting to fall apart. Then they pack explosives around them and slam them together, and then they just take off. And what takes off is all the white particles, which is just a million electrons surrounding it. You know, I say a million, bazillion, trillion, bazillion, millions. And pew, out they go. The first thing you're going to see is this house is going to light up like just brilliant. And then you're just going to see it vaporize. Now, I have this is already slow motion. And then I put it down to 25% speed. Watch what happens. Alright, out comes, boom, that's when the bomb went off. Here it goes, it's just burning, it's just burning. There's no concussion, nothing. I'm going to stop it right here. You see, in a second I'll get it going again. But why is this just burning with no, you know, this is a nuclear explosion. How come it's not moving? Well, the reason is, as I showed before, these are point particles. The outside white ones have literally no mass to them that I can determine. All they are is a burner. They just burn. You know, there's a push to it, but not much at all. Watch what happens now when the black ones, which are the ones that follow it, are the bowling ball ones that are never change size. That's the key. These can swish down little, get huge, no mass. The other ones have a huge mass and they can't move size, just one size, like a bowling ball. And here they come. Here it goes. Alright, it's continuing to burn, just burning, having a nice time, burning up, and then all of a sudden, boom! Now watch what happens. I'm going to stop it again. This isn't burning. The other stuff burnt like crazy. This isn't burning at all. And it's moving out, and you would expect any blast to just keep going. Well, it doesn't. It goes out, and now it wants to come back. And why does it want to come back? Because the dark matter here is now alone, back on the parade field where they blew the bomb up from. And now it's trying to drag all this stuff back to it to become, because now this is like gravity on the parade field. Normally it blew off all of the white stuff first, and then it was followed by some of the black stuff. But most of the black stuff stayed in the center. And now it wants the white stuff coming back. Watch what happens. It's gonna, you watch it carefully. Here it goes. It went out, and now it's actually stopping. And now it's turning around and coming back, right towards us. Alright, so as I showed you, we have two separate sources of energy. We have a burner and we have a banger. These bang, these burn. Let's think how we can use that to create free energy. I think we can use the burner, and instead of letting it burn something, we absorb it. If it doesn't burn, it gets absorbed. If it gets absorbed, we can use it to create energy. Okay, final statement. If this would create energy, we are golden to the world. we would know within 30 days if we really whacked at this thing. Like I said, it's in the design, and it's in where the laser sits, it's in the power of the laser, the frequency, and then the harvest. All of these things are readily available to be worked on and experimented with, and within a week or two or a month tops, we'll know one way or the other. Either I'll be the biggest laughing stock in history, or we're going to be able to go off to the races, and maybe, who knows what, we could have peace maybe. That would be nice. If everybody had their own energy, why would you go invade somebody?